everybody. It is Tuesday night, and I am recording a lesson for next week for AP Physics C and IB Physics HL. And Bugger is going to sit on the floor next to me. He's going to give me a num-num before I put him on the floor. Good boy. You are such a good boy. Oh. Okay, so let's go ahead and get started. Whoops. Okay, so what we're going to talk about right now is what are called RC circuits. Okay. And so let's just imagine that you have a circuit that has a resistor and a capacitor in it. So it has a resistor and a capacitor. All right, and that's it. So the resistor has a resistance R, the capacitor has a capacitance C. And if you think about it, this circuit has a single loop in it, okay? The circuit has only one current. There are no branches for the current to divide itself into smaller parts. There's only one current. So I'm going to call that current I. And I'm going to assume that that current goes in this direction. So that's the current I. So you might remember when we were talking about Kirchhoffs laws that for a resistor, the positive side of a resistor is the side that the current goes into. So this would be the positive side of the resistor. Similarly, the capacitor is the same way. So the side that the current goes into is the positive side of the capacitor. Okay? Now, the voltage drop across a resistor is I times R. So that's Ohm's law. And then for a capacitor, the voltage drop is Q over C. Because remember, for a capacitor, the main equation for a capacitor is Q equals CV. Okay, so dividing both sides by C, we get Q over C. All right. So now what I'm going to do is I'm going to apply Kirchhoffs laws. Okay. Kirchhoffs voltage law, excuse me. So Kirchhoffs voltage law, and if I go around this loop, so that was the one where we said the sum of the voltages around the loop has to equal 0. Okay, so 0 equals, and then if I start here, I begin to go around the loop, and then I hit the positive terminal of the resistor. So I get plus IR, and then I continue around, whoop, and then I hit the positive terminal of the capacitor, so I have plus Q over C. And then I get back to where I started. So this is Kirchhoffs voltage law for this very simple circuit. It's called an RC circuit because it has a resistor and a capacitor. So I'm going to transform this equation. All right. So the first thing I'm going to do is I'm going to subtract Q over C over to the other side, like this. And then I'm going to divide both sides by R. So if I divide both sides by R, I get Q over RC. And then I'm going to realize that current is the rate of flow of charge. So it's dq dt. Okay, so I'm going to plug that in right here. All right. Boom. So that is a differential equation. A differential equation for the charge on the capacitor as a function of time. All right. So that's nice. And so what I told you to do if you are solving a differential equation is you want to separate the variables. So my two variables based on this derivative are q and t. So I need t on one side of the equation, and I need all the q's on the other side. So I'm going to multiply dt over, and I'm going to divide both sides by q. So I have minus dt over rc equals dq over q. So that's called separating variables. And then once you've done that, you just integrate both sides. So I integrate both sides. The time goes from 0 to time t. And then the charge goes from q initial, whatever the charge at time 0 was, to whatever the charge at time t is. Okay? So r and c are constants, so this integral on the left-hand side is really simple. It's going to be just minus t over rc. Okay. And then on the left-hand side, this integral is natural log. So I get natural log of q at time t over q naught. All right. So then I can take this and I can solve it for q of t. And so to do that, I have to do e to both sides and then multiply the q naught over. And so what you get is that the charge as a function of time is equal to q naught times e to the minus t over rc. Okay, so it's an exponential decay of the amount of charge on the capacitor. All right, so if we were to graph charge on the capacitor as a function of time, it starts out at q naught, and then it exponentially decays to 0. Now, how quickly it decays to 0 depends on the resistor. The more resistance you have, the slower it's going to decay to 0. Okay? The less resistance you have, the quicker it decays to 0. So we can see that in the exponential here, t is compared to RC. So RC must have units of time because they're divided by each other. They're compared to each other in terms of size. So RC is often called the time constant. Okay, and it's equal to tau. All right. So yeah, so this is the charge as a function of time. And then we could also, from that, we could get other things, like we could get the current through the capacitor as a function of time. So the current through the capacitor as a function of time would be the derivative of that, so it would be dq dt, which would be minus q naught over rc, e to the minus t over rc. Can't remember if I said it, but q naught is the initial charge on the capacitor plate. And we're going to talk later on in the lesson about how do you figure out what is the initial charge on the capacitor plate. And then we could also do something like figure out the energy on the capacitor as a function of time, which is Q squared over 2C. All right. And so that would be squaring this. Squaring the exponential gives you e to the negative 2t over RC. So you end up getting Q naught squared over 2C e to the negative 2t over RC. Okay? So you can use this basic equation for the charge as a function of time to determine current and energy stored in the capacitor. So the energy stored in the capacitor obviously goes down as time goes on because the capacitor is discharging through the resistor. So like if this resistor were a light bulb, you would see the light bulb be very bright at first and then it would dim as time goes on. Okay. Now we can have circuits like, for example, this. Like what if I had a circuit that looked like this? Okay. Maybe this is R1, this is R2, this is C1, and this is C2. So this circuit can be thought of exactly like this circuit. Okay? What you want to do is you want to simplify. You want to combine the two capacitors into one. So if you have two capacitors that are in series, the total capacitance is going to be, so C sub S is going to be C1, C2 over C1 plus C2. So that's the series capacitance of 2. And then the series resistance is just going to be R1 plus R2. Okay. So if we wanted to know what is the charge as a function of time, well, the charge as a function of time would be Q naught e to the minus t over tau, where tau is the time constant, but the time constant would be the equivalent capacitance times the equivalent resistance. Okay? So it's going to be, RS times CS. So that's going to be R1 plus R2 times C1, C2 over C1 plus C2. All right? So that's how that works. So if you have combinations of things, like maybe you had something like this. What if you had a capacitor feeding into two resistors? Okay. So this is R1, this is R2, this is C. Your time constant, so it's going to obey the exact same form as a single resistor and a single capacitor, but it's going to be the equivalent resistance of these two. So your time constant is going to be R1 in parallel with R2, whatever that resistance is, times C. Okay? So you always want to identify for your circuit what is the time constant and then plug it into the general form for the charge as a function of time. So that's how that works. Okay. So sort of the next question. Oh, you know what? One thing I want to talk about before I do that is I want to talk about units. Okay. So kilo. I want to talk about kilo. I want to talk about milli. I want to talk about micro. So kilo is, of course, K. Milli is M. Micro is denoted by mu, or just a U if you can't do a mu. Nano, which is N. And pico, which is P. So these are all metric prefixes. Okay. So what do they all mean? Well, kilo means 10 to the third. Okay. Milli means 10 to the minus third. Micro means 10 to the minus 6. Nano means 10 to the minus 9. And pico means 10 to the minus 12. Okay? So these are really important to know. So for example, what if you had an RC circuit where here's your RC circuit, and maybe this is a 5 kilo ohm resistor, and this is a 4 nanofarad capacitor. Okay. All right. So what's going to be the time constant? Well, the time constant is RC. So it's 5 kilos. So that's 5 times 10 to the third times 4 nanos. So times 4 times 10 to the minus 9. Okay. So we can see that the 5 times the 4 is going to give 20. Okay. And then the 10 to the third times 10 to the minus 9 is 10 to the minus 6. 10 to the minus 6 is micro. So the time constant is 20 microseconds. Okay? So you need to know how to convert between these different metric prefixes. So if you have a kilo times a nano, then that's going to give you a micro. Similarly, if you had a kilo times a pico, that would be, 10 to the 10 to the third times 10 to the minus 12, which would be 10 to the minus 9. So that would be a nano. All right. So basically, the time constant sets the scale for how quickly the capacitor discharges. All right. So what this means is if the time constant is 20 microseconds, then that means, after 100 microseconds, that's 5 time constants, the capacitor is going to be completely empty. So if you waited a full second, that's many, many microseconds. So this capacitor is going to be completely drained even after a full second. So it kind of sets the scale for how fast this circuit is going to operate. Okay? The smaller the time constant, the faster things happen in that circuit. So that's really important. All right. So we know that the charge as a function of time is Q naught e to the minus t over tau. So we know how to get tau because tau is RC. Okay? We know how to get tau. But the question now is, how do we determine Q naught? All right. So how do we determine what the initial charge on the capacitor is? And so to do that, what we need to know something, which is that after a long time, okay, after a long time, a capacitor will block current, okay? And the reason is, so basically, it'll block current because it becomes fully charged, all right? But to sort of understand why a capacitor will become fully charged, like you can imagine a capacitor, it's these two metal plates, okay? So if you have current going into a capacitor, let's say you have current going down, then what you're doing is you're taking positive charge and you're piling it onto the top plate. So if you put a positive charge onto the top plate, then it pushes a positive charge off of the bottom plate so that you have negative on the bottom plate. And then you push another positive charge on, which pushes another positive charge off the bottom and leaves a negative behind. You put another positive charge on the top, and then that pushes another positive out the bottom, which leaves a negative. You put another positive, negative. Okay. So what you can see is that as the capacitor gets charged, you have positive charges piling up on this capacitor plate. And positive charges repel each other, right? Opposites attract, likes repel. So each additional charge that you pile onto the capacitor plate is more difficult than the last because the next positive charge now is repelled by 4. And if you manage to get it onto the capacitor plate, then the next charge will be repelled by 5, and so on. So it gets progressively harder the more charge you put on the capacitor plate. So eventually, the capacitor gets fully charged, okay, and the current just stops, okay? So, for example, what if you had a circuit like this, okay? And so maybe this is a 5 ohm resistor, this is a 12 volt battery, this is a, I don't know, 10 nanofarad capacitor, okay? So after a long time, all right, after a long time, the current through the capacitor will be 0 because the capacitor is fully charged and it will block all the current. Okay? So that means that the current has entirely stopped in this circuit. So the capacitor will eventually stop all of the current. All right? Now remember how the voltage across a resistor is I times R. So because the current is 0, that means that the voltage drop across the resistor is now 0. Okay? All right? Because the current got blocked by the capacitor. At first, it doesn't block it, but after a long time, the capacitor will eventually stop the current once it is fully charged. Okay? And once it does that, by KVL, okay, the sum of these three voltages has to be 0. All right? And we know that the voltage across the resistor is 0. So if the sum of all three of these is 0 and this one and one of the three is 0, that means that the voltage across the capacitor has to be equal to 12 volts because that's the only way they could cancel each other out. They're equal in magnitude, okay? So the voltage across the capacitor has got to be 12 volts, okay? Because this one is 0 and all three have to add up to 0. So if you have three numbers adding up to 0 and one of them is 0, one of those three numbers is 0, then the other two have to cancel each other out. And then the voltage across the capacitor is Q over C. So Q over C equals 12. All right. All right. And then, so that means that Q equals 12 times C. So that would be 12. That would be 12. Now this isn't kilovolts or nanovolts, it's just to the 10 to the 1 power. So 12 times 10 times 10 to the minus 9. So that's going to be 120 nanocoulombs would be the charge on the capacitor after a long time. Okay? Let's do another one that's a little bit more tricky. All right? All right, something like this. So maybe this is 1 ohm, this is 2 ohms, this is 12 volts, okay? And this is 10 nanofarads, all right? And we want to know, after a long time, what is the charge on the capacitor? All right. And so what we want to do is, after a long time, we can ignore the capacitor because it becomes fully charged. So it has no current flowing through it. So we can basically just forget about the capacitor. It has no current flowing through it, so it's like not doing anything, okay? And if we look at this, if I forget about the capacitor, it looks like a 12-volt battery pushing current through 3 ohms of total resistance. So after a long time, the current is going to be 12 over 3, or 4 amps. Okay? So 4 amps is going to come out the battery. All right? And then that 4 amps is going to hit this junction, but none of it goes this way because the capacitor is blocking the current because it has become fully charged. So that means that all of the 4 amps continues through the 2 ohm resistor. Okay? So what that means is that the voltage of the 2 ohm resistor is going to be I, the current that it gets, which is 4, times its resistance, which is 2. So that gives you 8 volts. All right? Now, the capacitor, which is often just called a cap, is in parallel with the 2 ohm resistor. All right? So we have a rule. It's called SIPOV, and it means that series things have the same current, parallel things have the same voltage. All right? And we can see that the capacitor is in parallel with the 2 ohm resistor. So that means that the voltage across the capacitor is also 8 volts after a long time. All right. And then the voltage across the capacitor is Q over C. So that's Q over 10 nanofarads. And so we get that the charge on the capacitor after a long time will be 80 nanocoulombs. Okay. So that's how we determine the initial charge on the capacitor. So let's do a full example, and then we'll be done. Okay. Let's suppose we have a circuit that looks like this. Yeah. Okay. So, all right. Let me give these some values. Let's say this is 10 kilo ohms. This is 8 kilo ohms. This is 4 kilo ohms. This is a capacitor that is 22 microfarads. Okay. And let's say that this is a 12 volt battery. Okay. So the switch, so this is a switch. So this switch can be in this position, or we can click it over to that position. All right. Like that. So the switch has been in position B for a long time. All right. At time equals 0, the switch is moved to position A. Okay. And what we want to do is we want to write the current, or sorry, the charge as a function of time across the capacitor, okay, for time greater than or equal to 0. Okay, so after we flip the switch. So what we need to do is we need to figure out, so we have this equation, Q of t equals Q naught e to the minus t over tau. So we need to figure out what is Q naught, and we need to figure out what is tau. Okay? So Q naught is determined by where the switch was before. Okay? So notice how if the switch is in position B, no current can go through these resistors because there's a dead end. All right? Any current that comes up through these resistors is going to hit the dead end. So we can just ignore the left-hand side of the circuit for time 0. Okay? So to determine Q naught, you really want to think about just the left-hand side of this. All right? Or I mean the right-hand side, excuse me. So we have basically this circuit. Like that. Okay? And the circuit has been like this for a long time. So that means that the capacitor is fully charged. All right, because it was in position B for a long time. All right. So basically we have, I did 2 examples of finding the charge on a capacitor, and it's kind of like this one. This is the situation. The capacitor is fully charged, okay? So it blocks the current, okay? So the current equals 0, which means that the voltage across the resistor equals 0. All right, which means that the voltage across the capacitor is equal to the voltage of the battery, which is 12 volts. Okay, now the voltage across the capacitor is Q over C. So Q over C equals 12. So we have, all right, so we have Q equals 12 times 22 micros. So that's 220 plus 44. So that's what, 264? Yeah. 264. And then it's a micro times 10 to the 1. So micro coulombs is the initial charge on the capacitor. Okay? So now we got to figure out what is tau. What is the time constant? Okay? So after the switch moves over to position B, then we can forget about the right-hand side of the circuit. So now the capacitor is going to discharge through this resistor and these 2 resistors. Okay? So let me draw what the circuit looks like after the switch is moved into position B. It looks like this. Okay? So we've just forgot about the battery over on the other side. All right. So what we can see, remember, tau is RC. So how much resistance is this capacitor discharging through? Well, it's discharging through 4 kilos in series with 8 kilos in parallel with 10. Okay? So 4 plus 8 in parallel with 10. Okay? That's the resistance that it is discharging through. And then the capacitance was, so it's this many kilos times 22 micros. All right, so I'm going to do this calculation. I'm not going to show it just in the interest of time. Okay, so this is going to be 8.4 times 22 times a kilo times a micro. 8.4 times 22 is 186. All right, what's a kilo times a micro? Well, that's going to be 10 to the third times 10 to the minus 6, which is 10 to the minus 3, which is a milli. All right, so the time constant is 186 milliseconds. All right, so now I know what tau is. So then it's super easy. I can write the charge as a function of time. It's just going to be 264 microcoulombs, all right, times e to the minus t over 186 microseconds. Or milliseconds, my bad. I said it was milli. Okay, so that's my answer. But I want to go a little bit further. I want to just show you how you can do calculations with this. So I'm going to flip the page and copy that equation down again. 264 micro e to the minus t over 186 millis. All right. So what if I wanted, for example, what is the current at time equals 0? What is the current through the capacitor at time equals 0? Well, that would be the derivative evaluated at time 0. Okay? So I take the derivative of this, and I would get 264 micros, and then taking the derivative of the exponential function does nothing. The chain rule is going to bring down negative 1 over 186 milliseconds times e to the negative t over 186 milliseconds. Okay? And then we plug in time equals 0. So this becomes e to the 0, which is 1. So this part just goes away. And we get negative 264 micros divided by 186 millis. All right? So 264 divided by 186 is 1.42. And then a micro divided by a milli, well, that's 10 to the minus 6 divided by 10 to the minus 3. All right, which is 10 to the minus 3. So this is 10 to the minus 3, which is a milli. So the answer is 1.42 milliamps is the current at time 0. Okay. Another thing I could ask is what is the energy stored in the capacitor at 300 microseconds? So the energy evaluated at time 300 microseconds. So what I'm going to do, that's going to be Q squared over 2C. So the first thing I'm going to do is I'm going to figure out what is Q squared. All right. Or what is Q of 300 milliseconds? Okay. So that's going to be 264 micros. Okay. Times e to the minus 300 millis over 186 millis. So notice how we have milliseconds divided by milliseconds, so they cancel out. All right, and I just get e to the negative 300 over 186. All right, so this gives me 264 micros times 0.199. Oops, that should be 264. Which gives me 52.6 microcoulombs is the charge on the capacitor at that time. So that's what I'm going to then plug in to this equation. So I have 52.6 times a micro, which is 10 to the minus 6, And I'm going to write this out in gory detail just because you really have to be careful about these powers of 10, okay? It's q squared, so I have 52.6 times 10 to the minus 6 divided by 2, and the capacitance, I forgot what the capacitance was. It was 22 micros, so that is also 10 to the minus 6. So 22 micros, like that. So notice how this 10 to the minus 6 cancels this 10 to the minus 6. All right? And so we get 52.6 squared divided by 2 times 22 times 10 to the minus 6. So let's see what that is. That gives me 63 times 10 to the minus 6, and it's in energy, so it's in joules. So that is 63 microjoules. And that is the answer. Okay? So I hope this makes sense. Again, just to review, we came up with a differential equation for an RC circuit, which is a circuit with a resistor and a capacitor. And we got the solution. That solution involves the initial charge on the capacitor and RC, which is called the time constant. And the time constant controls how quickly the capacitor discharges. Okay? So in every problem, all you need to do is figure out Q naught and the time constant and then plug it into this equation. All right? So if you have questions, I'll be available in office hours or in the Zoom room. Okay? Bye-bye.